Okay, so we're going to, let's see, the June 2015, we're going to work on the open response now. Number 25 wants us to inscribe a square in circle T. There's a lot of ways to do this. With this software, I can't show you my compass tool, so I'm going to do the best I can with Geometry Sketchpad. What we're going to do to start with is we're going to pick any random point on this circle. Okay. Then we're going to create a diameter. And again, this is any random diameter you want. So we'll grab that point and just hide this ray. So right now what we have is we basically have one of the diagonals of the square. Okay. So maybe I'll label that point A and that point C because it's going to be the diagonal. It's not going to be the 2 points next to each other. What I'm then going to do is construct a perpendicular bisector of AC. It should pass through T, and how you're going to do this with your compass tool, a little tricky. We're going to center a circle right here at A, and what we're going to do is we're going to construct, let's see, we'll put a point. So what we're going to do is we're going to open up the compass tool from point A to here, and we're going to construct a circle. Maybe what I'll do is I'll make that dashed. Now you got to keep your construction marks. So what I will do is just keep that there. It's going to make it look a little messy. You probably only have to go, you only have to show a little bit of this, an arc of this circle. You don't have to show the whole circle. But we got to leave our work. That's our work shown. This right here. All right, now whatever this radius is, okay, whatever it is, I've got to use this same exact radius and draw a circle centered at point C. So we're going to construct that. And what you have is 2 points of intersection right there. Now that should pass through T. Minor human error might have you missing that, but it really should. We're going to construct this line, and that's a perpendicular bisector of AC. Well, got to be careful here. You don't want to use this point for your square. It's got to be a point on the circle. So we're going to go right there and right here. Now those are going to be points B and D. Now when you do this, don't erase your construction marks. You need to leave them in there. That looks a little bit, let's see, I'll construct that segment, and let's see, I'll change that to thin. All right, good. So now what we're going to do is we're going to connect all of these points, and now you have a square inscribed in a circle. That's one way to do it. These points, we'll label them. Those are going to be B, label intersection B, and label this one D. And that's your construction. Got to be really careful. It's really tempting to make that D, but it's really the one that's on the circle there. Okay, so make sure we do that, and now we'll get out and move on. Okay, back over here. Now just remember what we did was, on this number 25, okay, we chose any random diameter. You're going to sketch, or you're going to construct that with a straight edge. And then you're going to need the perpendicular bisector of that diameter. And wherever the perpendicular bisector of the original diameter hits the circle, those are going to be the other 2 points of our square. All right, moving on. Number 26. Let's see, parallelogram. So those two sides of the parallel. Yeah, that's what we want to use. We want to prove angle NLO, or explain why. NLO, that would be this angle right here. Okay, so this angle that's right in there is what we're looking at. All right, why is that 40 degrees? Well, let's take a look here. We could use, since that's 118, we could use this as 118. And we can call that x. Let's start with, all right, angle O, measure of angle O equals the measure of angle M, because opposite angles in a parallelogram have the same measure or are equal. Or congruent, whatever you want to say. All right, now what we have is, if you just focus now on LON, we have a triangle, and the three angles of a triangle add to 180. So 118 plus 22, you're looking at 140. 180 minus 140 is 40. Of course, you could show the algebra instead if you prefer that. You know, you could go that way. And then if you have to add this, maybe just to the measures of the angles of a triangle, add to 180. You know, just to make sure that we've fully explained it. All right. So we're going to graph this. All right. And we're looking to find partition a segment, basically, is this problem. And is it a, no, it doesn't look like a directed segment. Okay, they tell us from A to P has to be in a ratio of 2 to 3. Okay, as soon as you see the 2 to 3, we need to say for work, we could say it's 5 equal parts that we're going to split the segment into. As soon as you recognize that and mention that, you're starting to gain some credibility. So what I like to do, okay, use a straight edge here. Don't freehand it, because you could count too far over, which is really easy to do. Okay, so we got 10 across and 5 up and down. All right, if we want to make that 5 equal parts, each equal part will move over 2 in the x direction. So this is what I like to do. I'm just going to move over 2. And if I used a straight edge, it would probably be right there. So I'm off a little bit just because I'm not using a straight edge. If you do, you'll be a lot better off. So those are the 5, right there, 5 equal parts. And we've got to make simply 2 parts here, 3 parts there. Okay, so that's going to be our point P. And all we got to do is get the coordinates. I'm getting -2, -3. That's one way to do it. Fully, you know, graphing it, demonstrating it that way. So P has the coordinates -2, -3. And of course, there's algebraic ways, but let's just go with that. Plenty of work shown on the graph to justify. So, all right. Let's see. We're looking at angle of elevations formed by the ramp and the ground. So we're looking at that right there. We're going to call that theta, or x if you don't like theta. what I would do is a right triangle, so we're using basic trig. And it's going to look like your right triangle trig, that is. There's your hypotenuse, and this is adjacent. Go ahead and use your acronym, whatever your teacher says. I just like to spell it out, SOHCAHTOA. Looks like sine, because the sides involved are opposite and hypotenuse. So that's the most efficient one. So we're going to say sine of theta, some angle, we don't know what it is defining the ratio of two sides, 4.5 to 11.75. I like to have my students just convert that to a decimal. Okay, that decimal is 0.382979. And now, how does this work? Well, we want to get theta by itself. To get rid of sine, you have to perform an inverse operation. It looks like that, sine inverse, or arc sine, whatever you want to call it. All right, so sine inverse of 0.382979. All right, and that gets us theta, because sine inverse and sine kind of knock each other out, so to speak. And then what we're left with is 22.5183. And we want to go to the nearest degree. Tricky there, so we're going to say it's about 23 degrees. And that's it. All right, area of sector. All right, so the area in here is 12 pi. And they give us the radius. All right, so they want to know how big this angle is if we know the area of it. So what we would do on this case is get the area of the entire circle. This is at least what I do. So we're looking at pi times 6 squared, so we're looking at 36 pi. And the reason I don't change it to decimal is because this is in terms of pi. Now, what we have to do next is determine what fraction or portion of the circle is this sector. So the whole circle is 360 degrees. How many degrees for this sector? Well, if the entire circle is 336 pi, I like to look at it as part over whole, something like that, right? So the part of it that's in the sector is 12 pi. The whole thing is 36 pi. So when you reduce that, it turns into 1/3. The pi's knock out. Okay, let me just show you the work there. Common factor is 12, so that's how we get down to 1/3. It's 1/3 of the circle. That sector is 1/3 of the circle. So basically, I would say 1/3 times 360 is 120. Okay. Now, there's a lot of other ways to do this, proportions, things like that, but I just feel like that's the easiest way to do it. So this arc is 120 degrees, and we know the central angle has the same measure as the arc measure. So the measure of angle AOC is 120 degrees. Okay. And come down to 30. All right. So we're just going to use words here. There's no diagram, nothing. After reflection, the image is congruent to the pre-image. We know that. Basically, they want to hear you say something about rigid motion transformations. So we'll talk through this. Basically, if triangle A prime, B prime, C prime is the image of triangle ABC after a line reflection, I'm going to go with this. Triangle ABC can be mapped to triangle A prime, B prime, C prime, using a sequence of rigid motion transformations. Okay, when this happens, the figures must be congruent. So triangle ABC is congruent to triangle A prime, B prime, C prime. So say something like that. They just want to know that you know the terminology, rigid motion transformations. You could say something along the lines of, you know, line reflections, you know, keep the image and pre-image congruent. You might get away with that, you know. That's another option, but I think they really want that terminology. That rigid motion transformation is going to get you a lot of leeway there. So, all right, moving on to 31. Let's see, flagpole. All right, we're having some interesting trouble with this problem in our classes. Okay. For some reason, we've got students thinking the shadow is along here. Shadows land on the ground, and we'll assume that this is the ground. So a shadow is going to go from here to here. All right, if this is the flagpole, your shadow is going to be along the ground. Okay, so for this entire distance across here, that's going to be 16.60 meters. Let's see, the base of the flagpole. Oh, okay, so here's where he's standing. He's going to stand away from the flagpole, 12.45 meters. It leaves a little bit of space left. Okay, and so right here, he is 1.65 meters tall. His shadow lands the same place as the flagpole's shadow. So they land right there. They end right there, I should say. And we're looking for this. All right, so really simple. The first thing we're going to do is we're going to get this distance, 16.60 minus 12.45. Okay, so we're over at 4.15 meters. Okay, for this distance here. Now what we have to understand is these are both right angles, assuming they're both right angles, and of course they can both use this angle right here. So we have similar triangles, and with similar triangles, we can use corresponding sides are proportional. So we're going to set up a proportion with corresponding sides. I'll start with this. I'm going to use the 4.15 is to be careful. You have to use the entire distance here. The corresponding sides here are 4.15 and 16.6. Okay, so we've got your shadow lengths, basically. Those are corresponding. Now we'll go to the, you know, the height, so to speak. 1.65 over x, because that's what we're searching for here. So we got 4.15x equals whatever 16.6 times 1.65 is. And we'll type that in quick to get 27.39. And then we'll divide. So then we get the x is, let's see, we get 6.6. So the height of the flagpole is 6.6 meters. Let's just make sure, 1/10 of a meter. Yep. Okay. So that's what we want right there. All right, 32. We'll start with information like this. We want to mark the diagram based on the given. And EGB, that's this angle right here. Follow the path, E to G to B. So we're opening that up right there. Okay, so that's going to be 50 degrees here. Oh, DIG, so same, follow the path, 115 right there. Now, we're explaining why AB is parallel to CD, so don't assume they are. They're going to be, but let's not assume they are. Let's not use alternate interior angles right here. It's really tempting to say, you know, that that's 50 because corresponding angles or something else. We're trying to show that they're parallel. So let's go get evidence. Let's go that direction. Personally, what I would do here is probably I see a linear pair between these two, right? So what do linear pairs do? They add to 180 because they make a line, or yeah, 180 degree angle, straight angle, whatever you want to call it. So let's start with that. 180 minus 115. We're going to be at 65 right here. Okay, so next concept is we have an isosceles triangle here. So we're going to use base angles theorem. Basically, you know, your angles across from congruent sides are congruent. So that angle is going to be 65. Now what we have is a triangle. And very simply, we're going to add those. 180 minus 130 is 50. So this angle is 50 degrees right here. Okay, well that puts that right there. And if you look, let's say in these two positions, we'll use that. Those two positions right there are corresponding angles. So we can say angle EGB is congruent to angle, let's go with GHI, because they have the same measure. Okay, and then we can say line AB is parallel to line CD, segment, I'm sorry, CD. And that is because when corresponding angles are congruent, two lines cut by a transversal are parallel. All right. And last one we're going to do for this video session, actually we'll stop it right there. We're at almost 25 minutes. So the next problems we'll put on the next video. Thanks so much.